Good morning. So I will try to introduce a joint work that I am conducting with my colleague Meslem from Grenoble. And we are interested in state estimation, and we would like to renew to have a new way of seeing state estimation using interval methods. Classical outline anyway. Maybe a quick review. So state estimation, state observer, or the use of observers means reconstructing the state variables of a system, state variables that are not directly accessible through measurement. So we develop a technique that is called state observation. So half of the audience is very aware of this, and maybe not the other half. So I give some tips and some clues. So we will, in a way, we'll try to rewrite a dynamical system and tuned in such that it would eventually converge to the as in its behavior to the behavior of the true system. So in red there would be some artificial or artificial state variables of an artificial system that would eventually converge to the true set variables of the true system. Standard methods, standard techniques are quite numerous, and there has been a huge amount of work in this area. What is interesting is that they can have a tuning parameter, which is called the observation gain, and these gain parameters will be tuned such that the system may have a kind of certainty that the system will converge. So that's very interesting in general to have a kind of proof of uncertainty. However, there are some limited class of systems that can be used, and among the limitations are the fact that noise and distribution should be known, difficult to take account of model uncertainty, and the initial conditions can be anywhere. To the contrary, state estimation in a bounded error framework or using set membership techniques, we have a kind of alternative approach. We try to build something that would hopefully converge to something that will enclose the true system. And in the interval community or set membership community, we use a one-step ahead prediction correction algorithm. What is nice about it is that we can naturally take into account bounded uncertainties, and also poorly known models, for instance, but along with possibly bounded domains for initial state. So I will mainly focus on this kind of systems, the discrete time systems where the dynamical model is linear with control. Possibly with control. This is a discrete time system, and we have additive noise, bounded noise in the process and in the measurements. We assume that the initial conditions are taken in a bounded domain. Okay, so the objective of set membership estimation is to reconstruct a set of sets. So a sequence of sets at time k or tk that enclose the true state variables, and in a way that the set contains variables that are consistent with the system dynamics and also consistent with the measurements, or the measurement domains, the feasible domains for measurements. And of course, what we are aware now is that prediction is quite maybe one-step ahead prediction is easy, and for the inversion would use Civia, for instance. Just schematically, so the idea is given an initial domain, we'll use the forward dynamics to compute the reachable set, and then to use set inversion to compute feasible domain for the projection of the measurement onto the state variables, and then consistency between the two leads to the intersection of the two sets. This is classical one-step ahead estimation. Okay, so that's the state of the art anyway. Now, what are the drawbacks? One first drawbacks is, of course, the over-approximation that can be induced by axis-aligned interval computation. But the main problem is that there is no proof of convergence. When we use one-step ahead prediction correction, there is no idea about how it will converge or if it will converge. So this is the main motivation of this work, to see if we can have an idea about how to analyze the convergence. So the main tools for the idea are as follow. So we have a linear interval system, discrete time system. So the idea is to proceed with multiple step ahead prediction. Instead of computing the image one step ahead, we'll try to do it for several steps ahead. Hence the K here. It's not difficult to come out with this equation. So we can compute on the paper, of course, this image of the reachable set after several steps ahead. And then, so first remark, yes, of course, this expression has no issue with dependence effect, so over-approximation is reduced. There may be some wrapping effect in this evaluation, but this wrapping effect will act only once. Whereas if several evaluation of one step ahead will at each time include a wrapping effect. The second tool is as follows. So now consider the output equation. We can think of stacking all the output equations over a time horizon in the future from step K to the n step ahead. So we have a stack of outputs. Here, for instance, you can stack all the outputs, stack all the control, and we will come out with something that will exhibit the observability matrices. And this matrix is not singular under the assumption that the system is observable. So the idea here is to take benefit from this observability assumption of the pair AC to invert this stack of outputs and control, and to come out with a consistent domain for the state variable at time K. So we would have solved the set inversion without using any bisection strategy, no contractors. There is no need to use Civia here. Okay, so we get benefit from the structural information about the system. The system is observable, hence we can use classical techniques in observability analysis in a way that is to stack the outputs and then to inverse this matrix to recover the state variables that are consistent with the output. Okay, now how can we exploit this to build a new state estimation algorithm? So there will be kind of open loop stage. First end steps will be an open loop, and then from the end step, the first end step and further, we can do prediction correction as follow. So I think maybe. So we have a moving sliding window of n variables, and we will use the measurements in the n step ahead to contract the data at time tj, and then using the contracted tj, we will do prediction at time tk, and then do some correction. So the current time is tk. So in a way, we go back in time, doing something that can be regarded as a backward propagation. And for this backward propagation, we use observability matrix to do set inversion. So we can have a reduced or contracted domain for xj, which is a past value, and we will use, in fact, all the past values to contract this xj, and then using the contracted xj, we'll do a forward propagation to compute a new set, a new domain for consistent variables for xk, and then contract, and then use consistency between prediction and the available variables. Okay, so it's a kind of forward-backward over a moving horizon, and it takes. And the consistency is solved using the observability matrix. The nice thing about that is that we can come out with an upper bound on the size of the computed domains, and size in computed domains that will depend on n, the horizon, and also the uncertainty on feasible domains on outputs, and the domains on disturbance. So this kind of results are nice because they can give you a way to tune or to analyze the performance of the algorithm. So of course, if there is no uncertainty in the measurements and in the process, the weights will converge to 0. Okay, small example to illustrate or to evaluate the algorithm. Simple two-dimensional discrete time system with additive disturbance, and this is the kind of results we can obtain, and it can be, okay, it works. Of course it works. Now what is interesting is if we compare this to classical state-of-the-art techniques such as ellipsoidal-based approaches, you can see that the reconstructed state variables, this is the measurement, this is the measured variable, and this is the reconstructed one. And you can see the size of the intervals in red, the width in red, which is our method, is smaller than, tighter than the one obtained by ellipsoidal approach. And of the same size when compared to a zonotop approach. Computation times are quite similar. Voila. So it's it's a new idea in way we're investigating to have a renew fresh look to state estimation in a way to have take benefit from the structure of the system, and hopefully to come with proofs or conversions that can be used for tuning. And we plan to investigate this in the framework of event or self-triggered approaches to state estimation. Thank you.
Thank you. Do you have any question? Yes?
Yes, in fact I have two questions.
Yes.
First of all, I think the invertibility of the observability matrix is only given if you have a single output system. What are you doing to select the corresponding rows in the observability matrix when you have a multi-output system?
It would be to have several estimators in parallel.
Okay, and you're evaluating then all of them in parallel, or just
so
take a subset?
I would do. It would be maybe a tuning. It's a tuning step. Yeah, it's a good. Maybe I should add a line in the perspective. Say, okay, should we? How many output the domain should be used to make the, but I would think of using all of them. Yes, in parallel. Yes.
Yes, and the second question is, as far as I understood it, you assumed that the disturbance in the state equations is uncertain but temporarily constant. Otherwise, you couldn't factor out this term D.
You mean we assume that the model is discrete time, hence the perturbation also is somehow discrete or constant between two time instants. Yes, indeed. Which is, of course, not so light assumption. It's a quite strong assumption, yes.
Yes?
I have a question. So in the forward stage, you use a pure simulation, no server, no? It's just a pure simulation in the time window.
In the forward.
In the time window, no? So
yes.
you reduce the wrapping because they conserve the dependency between states and.
We reduce the wrapping because we put all the problems to the exponential of the matrix A.
And then you correct in the backward.
It's somehow very similar to backward forward or forward backward propagation.
But there is some difference if you consider from the beginning a Nürnberger observer and just propagate this in a time window. Is it similar?
My problem would be in the forward.
So you just have the observer, Nürnberger observer there, and then you propagate for time in the time window, like this time.
The idea here is to, in the backward, to exploit the observability matrix, and the forward to use the exponential of the matrix. So there is the control wrapping effect is the fact we instead of successively computing the image, we
I know, in the time window.
Yes.
But you can have in this A the real measurement. You use the Nürnberger observer or something. You can have a different A matrix.
Okay, you mean you could use.
So you
I understand.
And you have this time window. So
yes, of course, it would be interesting to do this, but we would like to have a kind of prediction correction approach without the gate. Otherwise, there are tools for tuning properly as Nürnberger observer EEW. But we would like to have something that there is no, because they can be used for instance, fault detection or something like that. So it's an assumption that we have only prediction correction. Don't those do.
Thank you.
I have a small question. When you say about the proof convergence for the width, I'm not sure I understand. Because you are able to bound the width.
You're right. We have a bound, an upper bound on the.
At the beginning, I was thinking that you were able to
tune
that you will converge to the actual trajectory. But in fact, yes, you are able to bound.
Yes, but it's just to make sure that everyone agrees. I mean, the true state is, and if the assumptions are correct, the true state is in this box. It is in the box. So if we were able to prove that the width is tends to 0, it means that we have converged. Yes. Okay. So here we have an expression that depends on n, and the matrix A and O. So according to the structure of the system, we can have an idea about how large is the width. So we could hopefully think of tuning, for instance, the only tuning parameters here is n.
Okay.
So,
okay.
But of course,
the better n is to start from the beginning, not from zero.
sorry?
The better n is to have from zero. Time window starting from the initial state in the end.
Infinity, if you say n.
Yes.
Yes, but then, yes, of course.
Okay.
Thank you.
Thank you. Thank you.